Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about susceptor heating. So let's dive deep into this weird world. Well, what exactly is the problem that we have to put susceptor into it? Many things require very high temperature, and I mean high, as in most metal will be liquid by then, as in above 2000 degrees Celsius. Like high temperature ceramics, fiber optics, silicon technology, lot of things are like you start at that sort of temperature. Normal metal, iron, all of those things are liquid by then. So that's a very serious issue. And you're like, okay, can't we just use heating element, high power heating elements? Well, here's a problem. There has to be a temperature gradient for heat to flow. For example, if your target is 2000 degrees Celsius, your heating element must be above that, only then the heat will flow. If that flow rate is not matched, either A, it will take too long, or B, it will simply not heat up. So that's a very serious, like you can notice that in your soldering iron, things of this nature, because like if the solder melts at as low as like 230 degrees Celsius, why the heck irons need to go to 400? Well, if they don't go to even as low as like 300, it will take too long to melt. Heat will not flow. So fundamentally, you have a fundamental limit with normal heating elements. Even with infrared lamps, where the energy is coming from, it's coming from the filament. If filament heats up too much, it will get damaged, boil off. Basically, electron will physically boil off. All of those will cause a fundamental issue where it's like, nope, it's not gonna last long enough. Basically, it's gonna burn out and fail very quickly. Specifically, if you go above 1000 sustained, meaning till 1000 you can push it. 1100, not too bad. The moment you start to touch 1200, 1300, it's like, nope, no sir. So, and sometimes you also require what we call isolated or inert environment. For example, what if you do not want to rely on convection or conduction? What if you only need to rely on radiation? Again, you have limitation. Normal bulb filament cannot get hot enough. Other things will also not get hot enough. And if you're like, okay, what if I replace the strand with carbon fiber and then let it get hot? Yes, the capsulation you have, the quartz glass, that will start to melt. So how the heck you will melt something that requires quartz glass melting temperature? So there is a fundamental engineering limitation. It's like the moment you have to go much higher temperature, it's like almost most thing you will think of will fail. So, and sometimes when you are talking about a really bonkers high temperature, there is a problem of power density. As in, higher the temperature, the more brutal the heat outflux becomes. For example, you cannot have a chamber where it's like, okay, I have this chamber, I'm going to put a 10 watt of heat per hour into this, and this chamber will go to bonkers temperature. No, it will get hot as long as insulation is keeping up, but as it will reach a equilibrium, basically 10 going in, 10 going out, there will be equilibrium. How good your insulation is, that will define whether it's 70 degrees Celsius or 270 degrees Celsius, but it will not go to 1000 degrees Celsius, because the moment you increase the temperature, the push, the oomph that is going outside goes exponentially higher to the power of 4. So that fundamentally defeats any low oomph device, meaning you have to dump bonkers amount of power. For example, if you are talking something that is like dealing with ceramics, high-end ceramics, you are looking at 50 watt per cubic centimeter. You must be able to pump that much energy. Why that much? That's generally your insulation weakness. So basically, insulation is not like a wall, it's like a sieve. So when you start to pump pressure into this, it starts to leak faster and faster and faster and faster. So you must be able to outcompete it. It's like, oh, it's leaking at, let's say, a rate of 30 watt per cubic centimeter. I must be able to put 50 cubic watt per second. Only then you can rise the temperature. And God help you if you have to do that on a industrial process with something active, or something is actually taking the heat away. Like let's say you are cooking a fluid and you have to dump bonkers amount of temperature into it. But again, that fundamentally means the liquid is taking heat away. So how the heck you might have to exceed this also. So at high heat, insulation becomes just a suggestion. That's physics based. You cannot cheat it. So without massive influx, you will reach what we call stall temperature. Meaning you can test it, like all kilns that you can buy, you can put it on full power, close the lid and forget about it for a few hours or even days. Generally, they do that for outgassing and all that. It will reach a maximum temperature and you will know that it cannot cross that temperature. Like no matter what you do, it will not, because the outflux will match the influx. So if you want to do bonkers temperature, yeah, the normal conventional heating systems simply will not work. So the logic is, what if we change the medium rather than using photons or resistive heating? What if we utilize some material that is good absorber of electromagnetic forces, as in either induction or microwave radiation? Basically, that becomes our energy dumping medium. Now, you know, right? We use induction for a lot of things. Induction furnace is a normal thing. Problem is, it only works with conductors. It does not work well. Like if you have to melt zirconium with it, zirconium would be like lol. The zirconium will just lol at you. So there are a lot of things where it will, and again, glass crystals and all that, it's like lol. So induction will not do. Microwave will also not do anything. So you need a way of converting it. We have energy. If you want bonkers amount of energy, like 10 megawatt of energy in a small space with an induction field, we got that technology. That's not an issue. Issue is that that induction will not couple to glass fiber, or it will not couple to zirconium, or it's not coupled to certain silicons. It will just not care. It's like lol. So we need something that converts it. So here comes that material. That subsector is a bridge. Basically, you have the induction coil, and then you put the crucible. Now, crucible is made out of something that absorbs all the electromagnetic energy or field energy, and then dumps it as a black body radiation. Basically, this puppy starts to re-radiate all the energy. Again, you dump energy into something, it will try to seek equilibrium. To seek equilibrium, it must dump the energy. How will it dump the energy? Photons. So that's how you are heating the subsector, and that can be done without touching. Thou shall not touchy. And why go through all this hassle? Well, again, at high temperature, this is the only way to achieve it. Because again, induction coil can be cold enough where you can touch it. And again, even on a massive one, they generally have a cooling water going through it. And again, you must understand that it cannot be 2000 degrees Celsius if you have water flowing through it. No amount of pressurized water will be able to stay there. So, because the magnetic field has that energy is selective. And that's the key part. That energy is there in the free space, energy is there, but it will not radiate like a infrared lamp or a conductive heating lamp. It will not force through insulation. It will not force through vacuum. It does not care. It's a free space, and you can create a concentration of it by utilizing crucible. Crucible has to be made out of a material that is susceptor. Now, heating the susceptor without touching, microwave induction and all that, and energy that you want to dump is done via conducting aspect, as in it ignores everything else. So for example, if you are working with something that requires massive insulation, right? You have to have insulation, have the insulation between this, and then put crucible inside it. The crucible will melt without any issue. Insulation will not be touched. You're not forcing energy through the insulator. So because of this one-way valve technique, you can achieve bonkers high temperatures. Like you can have a tabletop crucible that can cross 1600 degrees Celsius like it's nothing. It's like, bro, don't even bother with me. So that's super easy to, and the core aspect that you can separate the heat and electricity. The electrical part is completely somewhere else. Okay, it could be completely up, and it is important because again, if you are dealing with some sort of industrial process, going offline is not an option. So it must require electronics that are like put it and forget it. That means robust cooling. You can't cool something if it's next to 3000 degrees Celsius. So these things allow you to do that. It's like, hey, coils are far away, man. Coils are far away. You have insulation. Then you have the crucible. Then you have the stuff that is hot. And crucible is almost leaching energy from the free space and heating it up. So because of your distance, your electronics is cool, your emission coils are cool. With microwave could literally be on the other side of the building if you want. So this isolation cavity that you get, like from an energy point of view, this is key. Like, can't I do that with IR? No, because if you are dealing with IR, you have to figure out transparency of material. For example, if you have to melt silicon fibers, glass fibers, so to say, yeah, the issue is it will not see infrared. Like you have a lamp, I'm going to pump energy into it. It will go through it. It will not react. At that point in time, you need massive broadband black body radiation, re-radiation. This takes care of that. This is the logic behind it. Do not dump energy directly because it can't be done. Like if you are dealing with aluminum, nobody will say do this. But if you are dealing with zirconium, glass, or any sort of ceramics that are touchy and they are like, no, I will not work with you, then this becomes a conductive option. It's like, I can dump energy into it and it will exceed any temperature metric that you can put on it. Like you can go 2000, like it's not even an issue. So when we are talking about susceptor, there are very strict list, so to say, because again, you do need something that is with very high melting point. For example, if you're working for some industry that requires 1600 degrees Celsius, your crucible, the bucket, must survive 2000 degrees Celsius. So again, heat must flow. The crucible is heating up. It itself cannot become liquid. So the requirement is very brutal. And not to mention, inertness is key. The moment you go into chemistry and you are like, okay, I'm dealing with 2000, anything above 1000 degrees Celsius, almost everything is violently reactive. Not reactive, violently reactive. And you're like, oh, it's a small stuff, it does not react. No, it's a brutal. Any and everything becomes violent at that point in time. So inertness is a difficult problem to solve. So you might be like, okay, what if I use this many things? You can use it. You just can't hit high temperature with that because it will become violently chemically active. It will go from I am inert, I don't care, to universal solvent best. So that's issue. Another aspect, we are talking about massive temperature, room temperature to stupid temperature of like 2000 plus. Yeah, it must not expand too much or contract too much because thermal shock will cause physical cracking. So it must be physically robust enough to handle the temperature gradient. And continuous bulk conductivity is the requirement for inductive systems. Meaning if you're like, hey, I'm using inductive heating source and I need a crucible for that, graphite is your guy. Great for that, but if you understood graphite and high temperature, you must have triggered a red alert. It's like, bro, graphite will burn. Yes, that's a very real world issue. You must flood it with nitrogen or argon or have it inside a vacuum. You fundamentally cannot have this just as like, tada, it will not work with tada. And not to mention, if you heat it up too much, it might even outgas, as in carbon literally might jump out of it. It's like, yee! So it might contaminate other things. So it is super easy, super cheap, very high temperature, and it has this weird property that if you heat it up to 2000 degrees Celsius, it becomes stronger. Super alloys cannot do that. We haven't even figured out how to make super alloy that gets stronger at high temperature. This puppy is like, oh, 2000 degrees Celsius. Finally, I can relax. Like it physically gets stronger at that temperature. So yeah, graphite is weird like that. So how the heck you deal with something like that? Graphite is not suitable simply because what if you cannot isolate it enough? Industrial processes, you can deal with it, but again, it's a dangerous mix, meaning your temperature must be controlled with gas flow. Gas flows are going, inert is there. The moment something happens, let's say your filter got clogged, gas supply cut, boom, cut the power, otherwise that graphite will become fire. So we use zirconia. Now, zirconia is inert with oxygen. It's like, it does not care. You can have this puppy 2000 degrees Celsius. It's like, bro, I don't even care. In open air, it does not care. So that's the great part. Problem is, it does not care at all. As in, if you're like, okay, I'm going to put zirconia, I'm going to turn on the inductors, nothing will happen. Nothing. It's like, nope, I'm not magnetically reactive. So how the heck we turn it on? Well, yeah, you have to preheat to 1000 degrees Celsius. That's its requirement. Thou shall heat it up to 1000 degrees Celsius. Then it's like, I'm going to react with magnetic field. That's up to you how to figure out how I'm going to have zirconia crucible and then preheat it. My best guess is they might be embedding carbon particles into it. Or have a donut, graphite donut inside it. Because once it's above 1000 degrees, it will start to interact, then it will have a runaway reaction and you can easily achieve 2000 plus without any issue. And these, so far I've talked about induction. What if you want to use microwave? Now microwave is wavelength, not magnetic field, it's wave. So it's a bit different. If you're like, you have a bulk material, it will backfire. As in like, I'm going to have this conductor. Does not work. So you need fragmented. You cannot have one continuous smooth bulk material. And it has to be micro thin. For example, if you put a aluminum bucket, lol, it will just lol it. Nothing will happen. But if it's micro thin, like microns thick, it will heat up crazy. So, and basically you need low electrical conductivity for microwave based heating. Now we do use that. It's super easy technology, as in like you may have eaten food from a box that was designed to go into a microwave, and that box, that could be cardboard, has basically coating inside it that cooks it. Basically you put it, if they say like, please cook in the package, that simply means it has a Susceptor coating into it. You put it in a microwave, microwave reacts very good with water. So let's say you have to make what we call choco lava cake. The cake outside must be cooked via infrared, but microwave only melts the inside. You will have that very soggy experience at that point in time. So the idea is the cup has this Susceptor. The cup cooks it. Physically, it absorbs the microwave, heats it up. So you are cooking the outside with infrared, inside with microwave. Tada, choco lava cake. So the utilization of this thing, well, a melting ultra pure silica glass. If you have watched my last week's video, ta-da! Basically, this is how we are making undersea fiber cables and all optical fiber. Basically, this thing has to be 2200 degrees Celsius. Yeah. Basically, this is one of the few things that genuinely reaches white hot temperature. Like, again, you can't fire infrared into it. Infrared will like, lol, I'm transparent to infrared. That's why you are using me. So you do need to create a what we call black body radiation, where it's like, I give you everything. And because it's a donut coming from all sides, it's smooth. Oh, and there is another benefit of it. Because it's a big, heavy, bulky thing, it also acts as a low pass filter, meaning electrical signals have high frequency into it. So whenever you are flowing something that is 100 meters per second, that temperature swing literally will look like, oh, fiber is fat, fiber is thin, fiber is fat, fiber is thin. That's not acceptable. So that mass of that susceptor allows it to act like as a buffer. Well, it does not allow changes to happen quickly. Semiconductor chemical vapor deposition. Like, to give you a context, there is literally 1 or 2 mines on the planet that can create crucible that is good enough to be consumed by silicon ingot construction. And yes, it is a consumable, because again, the crucible will react to the stuff. That's why I said, like, anything you go above 1000 degrees Celsius, everything is reactive at that point in time. And again, if you're 99.99999% pure, yeah, you can't just have anything. You have to use a sacrificial layer. That's quartz. So only this sort of subsector technology allows you to achieve that sort of uniformity of process. You can, let that be very clear, you can cook it in your house if you want to. It just won't, that like 99.99999% won't be there. Then you have Stirling Delta sintering. Basically, what if you have a lot of powder attached via binder? It's not good enough for human teeth application. So for my teeth like this, they will put it in a cooker like this. This cooker will pull a vacuum and then it heats it up 1600 degrees Celsius. At that point in time, those powder grain boundaries will start to merge with each other, and then you will get a crystal. That puppy is strong enough to survive your teeth, dental use. Basically, we have the technology to make amazing teeth. The one thing we don't have a way to bond this puppy to bones properly. Like my teeth, like you fire a bullet, bullet will bend. It's just that my face will break apart simply because of the energy. And again, even that is not that big of an issue. We don't have a glue that holds it. Like the doctor that placed it is like, yeah, I only give you a 10-year guarantee. I'll not give you more than that. It's like, what? Why? Yeah, the heating and cooling, the glue breaks apart. Like, can you imagine? That's our limitation of humanity. Is like, we can give you amazing teeth. We just don't have a glue that can work properly for 25 years or 50 years. So, amazing technology. And again, if you live in a small town, they will say like it will take 1 week for teeth to come. They are sending the teeth, the mold, the dental mold, to someone that has this machine. It's becoming common in India. It used to be like a monthly process. Now it's like, yeah, we'll get you in 3 to 4 days. Small towns. Major town, it's like, yeah, I'm going there, I'm gonna drop it off. And if you're like paying a lot, they can do it like morning, and they should be able to give you next day. Nuclear vitrification, because what if you have to melt something nuclear with something else and you have to do it inside a radiation shield environment? You cannot have the radiation coming out. Well, imagine covering everything with lead and voila. This allows you to put susceptor where it needs to be, and then you melt it and voila. Now you have radioactive waste turned into glass, which is stable, long-term stable. And microwave food packaging, you can buy this. This is the funny part. You can buy it. And not to mention, that's why I said the cup. Cup is a very common thing. I'm pretty sure you must have seen it. I guarantee it, you have seen it or have eaten from it without even thinking about it. Like, this is disposable. Like, sometimes it's scary how good humans are. Oh, we have this magical technology, we just throw it away. So utilization is there. Let that be very clear. Many things like internet will not exist if we have not mastered this furnace. So in the future, you have to know this is what we classify as critical technology. As in, like, we don't talk about it, but we assume you have it. Like, assume, done. I'm assuming that if I asked you to melt something at like 2500 degrees Celsius, you're like, yeah, I know a guy. That should be the answer for a country's point of view. It should not be like, yeah, actually we don't. That should not be an option. And carbon fiber has this unique ability that we are using it everywhere. Heck, we are trying to make rockets out of it. So Airbus is making like, carbon fiber panel. We have been making it for quite some time. Here's the issue. How the heck you weld it? Well, you can't. You drill it and you rivet it. Yeah, that's a wasteful, and not to mention it makes it brittle at that point, because again, the strands, as long as strands are intact, they are like great. But as long as you drill through the strand, it's like that part becomes a stress concentration. It's weak. So the idea is we can do subsector because the carbon fiber itself is that conductivity, where it's like it's not too conductive, so it will just ignore the fields, but it is not resistive enough where it's like completely useless, like it's not glass. So using induction welding, we can heat the fibers itself and then allows you to bond two plates with each other. Now, like, be mindful, we are talking about thermoplastic materials, not thermoset. For example, if you have epoxy based system, those are thermoset. They do go through chemical reaction, done. You can't do anything to it. You cannot weld it. Thermoplastics, basically using PEEK. Basically, you have carbon fiber strands and PEEK as the cement. Basically, your rebars is the carbon fiber, cement is the PEEK. PEEK is very strong, like GG strong, but it does need some structural binder to give it like the GG strength. Carbon fiber is there. But what if we can bond two panels with each other? Now, ideally, you will make it into one, but engineering is like, yeah, you can't spun up a whole Airbus A380 in one go. Good luck with that. So how the heck you bond it? Old school, have giant flanges, bolts and all that. Like, yeah. What if you can weld both of them? What if you have a whole panel going and then you're running this through it? Because PEEK will melt and the strand will get hot. Now, be mindful, strand is encapsulated in plastic, so it's not reacting with oxygen. Second, the PEEK plastic generally starts to liquefy at 350 degrees Celsius. Again, it does not become liquefy. It's like paste. So you can apply some physical pressure. And if you do this correctly, you get a bond that is very, very strong. And again, I'm reasonably somebody will figure out like to make the edges of panel in such a way that strands are interweaving, and then you just go ta-da. So this will be the future where aeronautics industry and rocket industry will utilize that. Rocket Lab is almost trying that, where they have that heated tape machine. The idea with that is they're using infrared lasers. Yeah, they're using infrared lasers to liquefy them. But right now they are on thermoset binder. Basically, it's making it tacky. They lay the tape, then they pull it in a vacuum bag, pull the vacuum, compresses everything, heat it up, ta-da. Once we reach this is what Airbus is working on right now. Once we reach that, you don't have to do that. Like, once you do the construction, the end, done, go home. It's almost like how metal welding is done. Like, you weld the metal, the end, you don't do anything afterwards. Same thing. So many industries are also figuring out, hey, we can use this to cook. For example, if you go to many industrial processes, especially things that are hot, like above 1200 degrees Celsius, they're like, yeah, electricity is no point here. We have to use fire. You really need very high temperature. Susceptors is like, what if you don't? What if you run your gas furnaces in night, but in daytime, you're in India, you have free solar, like almost free. That's how cheap it is, right? Indian government is like, from 2024, please consume more power in daytime. We have so much of it. So it's like, hey, what if we run this, that? But again, how would you reach high temperature? And again, this is industrial. It has to go, the flux, that has to be there. It's like, okay, susceptor, we have induction. Again, that's a sorted technology. We put susceptor around the pipes. Voila. You can go bonkers high temperatures. And again, this also have the unique advantage. Like if you are cooking something, what if you put susceptor into the material, and benefit of that, you cook from not outside in, inside out, or like, uniformly. And there are certain things that are like, if you can do that, shut up, take money. There are people claiming that utilizing this sort of technology, the unique ability of microwave to couple to susceptor, they can convert basically waste into hydrogen. Now, can they do that? Again, physics is not stopping it. It's just that I do not understand the energy balance. Again, it can be done. I'm like, I would not be shocked if, like, it's at the end of the day, you're dumping energy to break the bonds. It's like, duh. How they are doing it energy efficiently, that's the key part. And some are like saying, hey, we can do instead of steam reforming, we can do that same thing with electricity, and that would be far more efficient. That's cool. So again, it's unlocking a thinking process that you may not think about. Like if I say, oh, 1000 degrees Celsius or 2000, it's like, who cares? It's like, no, everybody cares. It's like for industrial processes that I can give you above 1000 or above 2000, and you don't have to think about it. It's like, oh, it's just a thing. So many new avenues open up on chemistry and industrial processing. Shut up, take money. And if you can do that with electricity, cheap solar, done. So future is very interesting of this technology, like very interesting. It's like we did not almost care about it. Now it's like, oh, you can't watch internet without it. I can't have my teeth without it. So it's cool. So this was my presentation on susceptor heating. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you have enjoyed it, click the like button. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show makes appointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.